Hello everyone, this is Bukya Krishna, rule number 20951A2130, branch aeronautical engineering. So today I want to discuss about combustion of liquid propellants. Introduction. First I want to discuss about what is liquid fuel combustion. In general, the combustion of a liquid fuel takes place in a series of stages: atomization, vaporization, mixing of the vapor with the air, ignition, and maintenance of combustion, that is flame stabilization. Recent advances have shown the atomization step to be one of the most important stages of liquid fuel combustion. Liquid propellant rocket. A liquid propellant rocket or liquid rocket utilizes a rocket engine that uses liquid propellants. Liquids are desirable because they have a reasonably high density and high specific impulse, that is ISP. This allows the volume of the propellant tanks to be relatively low. It is also possible to use lightweight centrifugal turbopumps to pump the rocket propellant from the tanks into the combustion chamber, which means that the propellants can be kept under low pressure. This permits the use of low mass propellant tanks that do not need to resist the high pressures needed to store significant amount of gases, resulting in a low mass ratio for the rocket. So this is the diagram of the rocket, which contains of. So this is the simplified diagram of a liquid propellant rocket that describes the first one liquid rocket fuel, second one oxidizer, third one pumps carry the fuel unoxidized, and the fourth one is the combustion chamber mixes and bonds the two liquids, and the fifth one is the gas put off by the reaction passes through the throat, which aligns all the gases produced in the right direction, and at last exhaust exits the rocket. An inert gas stored in a tank at a high pressure is sometimes used instead of pumps in simpler small engines to force the propellants into the combustion chamber. These engines may have a higher mass ratio but are usually more reliable and are therefore used widely in satellites for orbit maintenance. Liquid rockets can be monopropellant rockets using a single type of propellant or bipropellant rockets using two types of propellant. Tripropellant rockets using three types of propellant are rare. Some designs are throttleable for variable thrust operation, and some may be restarted after the previous in-space shutdown. Liquid propellants are also used in hybrid rockets, with some of the advantages of a solid rocket. And the next one is principle of operation. All liquid rocket engines have tankage and pipes to store and transfer propellant, an injector system, a combustion chamber which is very typically cylindrical, and one sometimes two or more rocket nozzles. Liquid systems enable higher specific impulse than solids and hybrid rocket motors and can provide very high tankage efficiency. For injection into the combustion chamber, the propellant pressure at the injectors needs to be greater than the chamber pressure. This can be achieved with a pump. Suitable pumps usually use centrifugal turbopumps due to their high power and lightweight, although reciprocating pumps have been employed in the past. Turbopumps are usually extremely lightweight and can give excellent performance with an on-earth weight well under 1% of the thrust. And the next one is combustion stability. To avoid instabilities such as chugging, which is a relatively low speed oscillation, the engine must be designed with enough pressure drop across the injectors to render the flow largely independent of the chamber pressure. This pressure drop is normally achieved by using at least 20% of the chamber pressure across the injectors. Nevertheless, particularly in larger engines, a high speed combustion oscillation is easily triggered, and these are not well understood. These high speed oscillations tend to disrupt the gas side boundary layers of the engine, and this can cause the cooling system to rapidly fail, destroying the engine. These kinds of oscillations are much more common on large engines and plagued to the development of the Saturn V but were finally overcome. Some combustion chambers, such as those of The R25 engine uses Helmholtz resonators as damping mechanisms to stop particular resonant frequencies from growing. To prevent these issues, the R25 injector design instead went to a lot of effort to vaporize the propellant prior to injection into the combustion chamber. Although many other features were used to ensure that instabilities could not occur, later research showed that these other features were unnecessary and the gas phase combustion worked reliably. Testing for stability often involves the use of small explosives. These are detonated within the chamber during operation and causes an impulsive excitation. By examining the pressure trace of the chamber to determine how quickly the effects of the disturbance die away, it is possible to estimate that the stability and redesign features of the chamber is required. And the next one is engine cycles. For liquid propellant rockets, four different ways of powering the injection of the propellant into the chamber are in common use. Fuel and oxidizer must be pumped into the combustion chamber against the pressure of the hot gases being burned, and engine power is limited by the rate at which propellant can be pumped into the combustion chamber. For atmospheric or launcher use, high pressure and thus high power engine cycles are desirable to minimize gravity drag. For orbital use, lower power cycles are usually fine. Some of them are pressure fed cycle, gas transfer cycle, expander cycle, stagnation combustion cycle. The next one is cooling. Injectors are commonly laid out so that the fuel rich layer is created at the combustion chamber wall. This reduces the temperature there and downstream to the throat and even into the nozzle and permits the combustion chamber to be run at a higher pressure, which permits a higher expansion ratio nozzle to be used which gives a higher ISP and better system performance. A liquid propellant engine often employs regenerative cooling, which uses the fuel or less commonly the oxidizer to cool the chamber and nozzle. Conclusion: in a liquid rocket, stored fuel and stored oxidizer are pumped into a combustion chamber where they mixed and burned. The combustion produces a great amount of gas at a high temperature and pressure. The hot exhaust is passed through a nozzle which accelerates the flow. Thank you.